I'm going to start in the name of God. Welcome back. Last time we've seen like a general introduction about this subject, which is, one second, it's all about kinetic theory of gas. A general introduction was made, and then a lecture introducing or reviewing the concept of probability. And I'm going to continue from there today with the following examples to build on what we have talked about in the last lecture concerning probabilities. So I'm going to put a new page here. So let's suppose that we have a system. No, I'm going to take a different color. Example, this should be a G. Let's consider a random variable x with possible values of 0, 1, or 2. So let x can be drawn from 0, 1, 2 with probabilities. So I'm going to write probabilities as p of x to be one of these, 1/2, 1/4, 1/4, right? And let's say we want to calculate the average of x and the average of x squared. Okay. The information which is giving is we have p of x, probability for each possible value of the random variable x. So x can be 0, 1, or 2. And the probabilities are like for 0, probability is 1. So if we suppose this point such that here is going to be the value for the probability 1/2, then I can draw hopefully a straight line here to represent that. When x is 1, the probability is 1/2. Let's suppose 1/4. Let us suppose that 1/4 is here. So for the case of 1, I have this, and for the case of 2, it's also 1/4. So I'm going to draw that here, right? So you can see the values are kind of the same for 1 and 2. And for the case of 0, the probability is 1 divided by 2. Okay. So the probabilities distribution is given completely. It's a complete information which one can use. So once this is known, as we have discussed earlier, then we can use the distribution to compute averages, like the average of ax and the average of x squared. As a first check, it's useful. So always do that. Check that sum over all the possible probabilities is 1. Is it true? Well, you can do that, and you're going to see that it's true because we have 1/2 plus 1/4 plus 1/4. Cancel that. That plus 1/4. This is going to be 1. So this okay. So So good check. Next, one can use the definition of the average value of x has to be the summation over I of xi pi. So this is going to be x1 is 0 times p1. P1 is 1 over 2 plus x2 is 1 times p2. P2 is 1 over 4 plus x3 is 2 times p3 is 1 over 4. So one can sum this out and get something like that to be 3 by 4. Hopefully correct. So the average of x is 3 divided by 4. Similarly, one can compute the average of x squared. Okay, I'll leave that for you to try if you want. So this example is an example where we have a discrete probability. The system is discrete. Let us look at another example where the system is continuous. Okay? For that, maybe it's better we go to a fresh page. The example is an example of a probability distribution called Gaussian. So we have a Gaussian probability distribution, right? And what is it? It's something like this. You have probability density p of x. Sometimes, loosely speaking, we say probability. So p of x is a constant c times exponential of minus x squared divided by 2a squared. Okay, so this is definition of the probability distribution. You can look up how that looks. You can plot it using Python to play with stuff, but I'm going to draw something by hand here. It's something like this. It's very rough, but approximately. So we have p of x here and then x. Okay, so you can see the probability of getting a number, say between x0 and x0 plus dx. So I've chosen an interval here. Dx, as we've mentioned earlier, it's going to be, well, the area on the curve within the chosen region. So the area here, I try to shade a bit here for you to see. Okay, so the setting of this example is that given this probability distribution, where maybe I write here c is a constant. Okay, how do you calculate the average of x and the average of x squared? Well, you can do that using the definitions we've got earlier, but to begin with, the definition is that once you know the probability distribution, then you can integrate, for the case of continuous variables, to compute averages, right? But would want to check first that the probability distribution or the probability density is well behaving, or in other words, if it is normalized or not. So if p of x, the x integrates to 1, then p is well normalized. So let's check for p of x, which is given above. If you put in the values, you substitute what px is. Px is given here. So let's try to integrate. If you integrate that over the range from minus infinity to plus infinity, so p of x is c e to the minus x squared over 2a squared dx. Yeah. And using a formula which we're going to talk about later, one can compute this integration. So c is a constant, it can come out of the integration, and when you do the integration, I'm just going to give the answer here, but in like a bit later we're going to show how this is done, or if you've seen it before, then that's fine. You just move forward. So the integration of e to the minus x squared divided by 2a squared is going to be square root of pi divided by 1 over 2a squared. Right, so I'm going to put this in the square root. Okay. And so this is going to be equal to c times square root of 2 pi a squared. Okay, so you can see that this is not equal to 1. Since this is not equal to 1, but we want it to be equal to 1, you can do so by fixing c to be the inverse of square root of 2 pi a squared. So if c is the inverse of that, then our answer is going to be equal to 1. Therefore, normalize, we say that p of x is normalized using c to be equal to 1 divided by 2 pi a squared square root. So this is square root and 1 divided by that. Okay, with this choice for the constant c, then we're going to see that the integration px dx would be exactly equal to 1. This is a check which we want to that it always happen. Using that, next thing is using the normalized probability distribution, then we can compute the average. Okay, so now we have p of x to be equal to 1 divided by square root of 2 pi a squared e to the minus x squared all over 2 a squared. Okay, and using that you can compute the average of x as follows. You've got the formula, we've discussed it, we discussed about it earlier. This is going to be x times p of x dx. So this is going to be bringing out the constant values out of the integration sign. I've got 2 pi a squared and the square root here, and then integration of x e to the minus x squared all over 2 a squared dx. So this is also something which has, I didn't say it, but the integration is done from minus infinity to plus infinity. And so the next thing is would want to do the integration. We want to find what this integration is going to be. Okay, Because of symmetry, the answer is actually going to be 0. So let me write the answer first, and then we're going to talk about why is it that it's going to be equal to 0. Okay. Actually, what's happening is that when you're doing integration, remember, integration is a continuous variable version of summation. So actually what we're doing is summing. We're summing things. We're doing summation over the x in the direction of x. So x is varying from minus infinity all the way from that all up to infinity. Let's assume we can write it this way. In between there is something 0. When x is 0, you can see that actually 0 times anything is going to be 0, so no worries. What I'm going to get is 0. But at other times, when x is negative, so when we're looking at this part of the line x, maybe we can call the integrand to be, just as an example, supposition. We can suppose that all we have here, for example, is minus a. So you're going to sum stuff. Things are going to sum up, you're going to sum them, and it's going to be minus a. But on the right side of 0, it's going to be plus a, right? And right at the middle where we have 0, it is 0. So why am I writing it this way? Like in negative x, I'm saying it's something minus a, and in the region positive x, I'm saying it's going to be plus a. The reason is that the function we're dealing with, the integrand, what we are integrating over here, is actually what is called an odd function. So an odd function is, what's the feature? The feature of odd function is that you get the same value depending on whether x is positive or negative. You get the same exact value but with opposite sign. So if on the right hand side of the 0 in the positive region of x, supposing all the summations turn out to be plus a, then all the summations on the other side, because x is negative, would sum to minus a. And then when you sum everything together, minus a plus 0 plus a, you're going to have that to be 0. So in general, whenever you have this kind of integration, you're in summing over an odd function over a region, say from x minus infinity to infinity. It's very important that you're dealing with both the negative side and the positive side in an equally or symmetric manner. Then the answer is always going to be 0. So I'm doing summation from minus infinity to plus infinity of an odd function. This is going to be 0, full stop, that's it. And the average of x is going to be what? It's going to be 0. I think I can still write here. So I'm going to do that for computing the average of x squared. The average of x squared is going to be integration from minus infinity to plus infinity x squared times p of x dx. Okay, and this is going to be like we've done above, 1 over 2 pi a squared. They're all at home in square root from minus infinity to infinity x squared e to the minus x squared all over 2a squared. So what's the answer for this? You can see that in this case, what we are doing, the integrand here, is actually what is called an even function, because we have x squared, which is even, undertaking x to minus x, and the part with exponential is also even. So we cannot use the reasoning we've done for the case here to say that the answer is going to be 0. So we have to work the integration out. Okay, how the integration is done is, if you wait a bit, maybe I think we're going to look at that. For now, I'll just use the formula. So there is a formula for that. If we just put in the formula, so this is going to be equal to 1 divided by 2 pi a squared all square root, which is the constant coming out of the integration sign here. And using some formula, the integration is going to be 1 over 2 times 8 pi a to the 6 all square root. Okay, and when you solve that, you're going to get the answer to be a squared. So the average of x squared is a squared. Okay, if we just be patient a bit, I'm going to discuss how this integration turns into this number. Okay, this is something which can be done. So what's the point here? Again, it's an example. We've looked at an example in this case for a continuous probability distribution. It has a special name because it is used several. Not because it is used. It has a name because it's an important probability distribution. You're going to meet it in so many places doing physics and statistics and probability calculations. Maybe you've done that already. Okay, I think that's it for this example. Given the probability distribution, you can compute the average of x, you can compute the average of x squared, and actually you can compute the average of any function of x, as we have discussed earlier. So the next thing, I think we should play more a bit. It's nice, it's sweet to see where the integration come from. Okay. So you can see that maybe if I go back to the previous page, try to connect with the subject under consideration. So the subject we're discussing about kinetic theory of gas. There are lots of number of molecules or particles in a system, and we want to describe the behavior of the system in an approximate manner using statistical techniques. Here we're using probability, and we want to compute averages. And for computing these averages, given probability distribution, we have to find the probability distribution in the case of a gas. We're going to see that later, I hope. And once we have probability distributions, as I have illustrated in these two examples, here is an example of a discrete for a discrete system, the probability distribution is known and you can compute averages. We've also seen this example of a continuous distribution. You're going to compute averages once the probability distribution is known. So computing integrations is going to be important later, and for that reason we're going to talk a bit more about this type of integrations. Already we've talked about one of them, that is how to do this integration of x times e to the minus x squared divided by 2a squared. You can see it's 0 as I have explained earlier. We can derive other integration formulas from this, and also where the answer for this integration comes from is going to be the next thing. I'm going to discuss here. So let's write something like pick a pen and then write. I think it's a bit up. So integration formulas. We have already solved the first one. Okay, so I'm just going to give the result here. We've solved it in the previous page. If I call the integration I to be the integration from minus infinity to infinity of x e to the minus x squared e to the minus some constant alpha times x squared dx, yeah, here with alpha a constant. Okay, we have seen that the answer for this integration is 0. It's equal to 0 for symmetry reason, as I have explained earlier. Okay. Next is integration, which I'm going to call it big I1. Supposing instead of integrating from minus infinity to infinity, we're going to integrate from 0 to infinity x e to the minus alpha x squared dx. What's the answer for this? Okay. For solving this, we do some revision on how to do integrations. So we change variable because of this symmetry here in the exponential. So we're going to let variable z be equal to alpha x squared. Once this is the case, you can do this to find dz is going to be 2 alpha x dx, such that then we can substitute x times dx, which is showing up in the integration. So we have x dx here. We write it in terms of dz. This is going to be 1 divided by 2 alpha dz. Okay, and you can see that when x is 0, z is going to be 0. When x is infinity, z is also going to be infinity. Therefore, we can write I big I1 to be equal to the integration from 0 to infinity of 1 over 2 alpha dz e to the minus z. And hopefully it's easier. You know how to integrate exponentials. This is going to be equal to 1 over 2 alpha. So this alpha is a constant, 2 is a constant. We bring them out of the integration sign. And when you integrate e to the minus z, the answer is going to be minus e to the minus z. But we're doing this integration from 0 to infinity. So you do the substitution, it's going to be 1 over 2 alpha into the e minus e to the minus infinity minus minus e to the minus 0, and your answer fully is going to be 1 over 2 alpha. So actually I1 is that. Okay, So this is a nice formula, something which we're going to use a lot. We're going to use later. And it's useful for the case, supposing x is a velocity, right? And or speed, when we talk of speed, speed has positive values. It's always from 0 to whatever value, maximum value it can take. So dealing with the velocities of gases, this formula is going to be useful. We're going to use it, and that's why we've given it a name. I1 is the integration from 0 to infinity of x e to the minus alpha x squared dx, and the answer for this integration is 1 over 2 alpha. Okay, nice. This is something maybe one can hold on and remember. Okay, so the next integration formula would like to consider is I call it I0. So I0 is equal to the integration in this case is from minus infinity to plus infinity e to the minus alpha x squared dx, right? So it's like a Gaussian. You can see a Gaussian here with constants, which we can see what they are, right? So we want to find what the answer for this integration is going to be. The method I'm going to show is the one where we try to square what we're looking for. So I0, whatever it is, if you square it, it's going to be something you can write like this. So you have two integrations from minus infinity to infinity, and you can use any name for the variables here. They are dummy variables. The x I'm going to use for the first one, e to the minus alpha x squared times another integration from minus infinity to infinity dy e to the minus alpha y squared. Okay, so this is like 1 I0 times another I0. Okay, it doesn't matter so much what it doesn't matter so much what we call x here, because we're summing over x. It's called dummy variable. Okay, if someone likes, we could have used x here instead of y, but I think it makes things more clearer to kind of differentiate if we use a different variable compared to the variable here. Okay, so to avoid confusions, and this way you can open one can open the bracket to see that actually the integration becomes something like this. So this is equal to, you're going to have a double integration from minus infinity to infinity of dx dy, and combining this exponential, the part with exponential, so this minus alpha, the constant, x squared plus y squared. Okay, so this is like kind of a area integration, and to do this integration it's much better if we sort of change variables from Cartesian coordinate system to spherical, or in this case two-dimensional. It's polar coordinate system. So what's happening is like we're doing some sort of summation, but this time around in a 2D space, so I can draw schematically here in the Cartesian coordinate system. I have x and y, and I have an elemental area where we have dx here and dy. So this is in the Cartesian coordinate system. This is Cartesian. Okay, and we can convert this, move that coordinate system into a new one. So for example, here the variable x and y, they both vary from -infinity to infinity, but for polar coordinate systems, it's a bit different, like points in the polar coordinate system. All right, polar coordinates, Cartesian coordinates. So here we can think of a point, right, which is x, y, represented by xy. In the polar coordinate system, points are represented by r and theta. So r is the length connecting the point to the origin, and the origin is 0, 0, right? So here we talk about r and theta for the point, and we can also represent theta this way. Is the angle between the line connecting the point and the origin with respect to the direction of the x coordinate system. Okay, so in the polar coordinate system, we have some sort of, the area is represented this way, kind of, right? So the area element is represented by, so if I change theta from theta to theta plus d theta, so maybe it's good, I'll try drawing here. So this change by an amount, yeah, which is d theta. Okay, so one can see that the length of the arc here is going to be r d theta. Okay, so the element, the area element is going to be approximately also length times width. Okay, so the length here, or the one on top, is r d theta. Okay, and the element here is dr. Okay, so the point moved, it changed from r to, say, this point, which is r plus dr, and theta plus d theta. Okay, so maybe I try to make it green here, right? So green point is r plus dr theta plus d theta. Okay, and the green point here is x plus dx, y plus dy. Okay. The black point, which is over here, is just xy, right? So there's a change from x to x plus dx, y to y plus dy. So we have the areas. So you can see there's a changing coordinates. This is what is happening actually. So r ranges from 0 to infinity. This is what values of r can take, and theta can range from 0 to 2 pi in units of radians. This happens for the case when x goes from minus infinity to infinity and y goes from minus infinity to infinity as well. Okay, so there is no way out. Maybe we have to go to the next page. So the relationship between the two coordinate system is that r squared is actually equal to x squared plus y squared. Okay? And the element area in the Cartesian coordinate system is x dx dy. In the polar coordinate system is r d theta dr, as we have seen. Okay, so length of the small arc times length of the small arc dr. Okay? Therefore, in this way, we can see that I squared is going to be, maybe I write it downstairs, is going to be, I think we can manage. I squared is going to be 2 integrations from 0 to infinity for dr and from 0 to 2 pi for d theta. Okay, something. So I'll write it again here in a smoother way. I squared is going to be equal to integration from 0 to infinity, integration 0 to 2 pi of the area element in the polar coordinate system is r d theta dr e to the minus alpha. Instead of x squared plus y squared, we're going to have r squared here. Okay, so you can see we can bring out the integration from 0 to 2 pi for d theta. Sorry, it can decouple. D theta, and then integration from 0 to infinity for r e to the minus alpha r squared dr. Okay. And this turns out very nice because part you can, I hope you can see that we know the answer for this integration. We have done it in the previous page. Let me see, is that true? Yeah, we have done it here. You can see the answer is going to be 1 over 2 alpha. Okay, so this is r e to the minus alpha r squared dr. So use r instead of x. So we have already known what the answer is for that part of the integration. So we're just going to put it in. And okay, let me use black here. So this is going to be, when you integrate the part of d theta, the answer is going to be theta, but you are integrating from 0 to 2 pi, and the part in yellow, as we have seen, the answer is going to be 1 over 2 alpha. Okay, when you do the substitution, this is going to be 2 alpha minus 0 times 1 over 2 alpha. Sorry, this is going to be 2 pi minus 0 times 1 over 2 alpha. So the answer is going to be 2 pi divided by 2 alpha. So this is going to be pi over alpha. Therefore, we now have our answer for I0. Sorry, it should be I0 squared. This is I0 squared. Therefore, I 0, which is the integration from minus infinity to infinity of e to the minus alpha x squared dx is simply going to be, is nicely going to be alpha, going to be pi, square root of pi divided by alpha. Okay, so this is another very nice formula which we're going to use a lot, like that one, written in green. So maybe I should have written the I0. So we have I1 and then we have I0 in green. Okay, so we have I0 and we have I1, which we have used above. Just to write it again, 0 to infinity, x e to the minus alpha, x squared, the answer is 1 over 2 alpha. So we have these nice formulas, two of them, and one can use them to derive some other integration formulas. Very nice, in a very nice way. I'm going to show an example which we can round up with. So let me write from I0 and I1, one can derive the other integration formulas that we call, for example, so from I0 you can get I2, I4 and so on, and from I1 you can get I3, I5 and so on. So you get the even ones from I0, you get the odd ones from I1. Okay, as an example, let us look at this one. If we integrate, if we differentiate both sides of this formula for I0, then we're going to get a formula for I2. Okay, so let us do that. Differentiate with respect to alpha on both sides of the equation for I0. So I'm going to write d by d alpha of integration from minus infinity to plus infinity e to the minus alpha x squared dx. Whatever that is, it has to be equal to d by d alpha of pi divided by alpha square root. Okay, and doing the differentiation, then we can get the formula for I2. So for example, this implies that I have integration from minus infinity to infinity of minus x squared. When I differentiate with respect to alpha, I get minus x squared e to the minus alpha x squared dx for the left hand side, and this is going to be equal to, I bring square root of pi outside, differentiate. The right hand side is going to be minus 1 over 2 times alpha minus 3 by 2. Therefore, we have I2. We define I2 to be something like that. Integration from minus infinity to infinity, x squared e to the minus alpha x squared dx. Okay, this is going to be equal to 1 over 2 square root of pi divided by alpha cubed all square root. So you can see nicely you get I2 this way. Okay, and if you differentiate again this formula with respect to alpha on both sides, you can get the formula for I4 I6 etc, right? And if one were to start with I1, differentiate both sides of this formula, then one can obtain a formula for I3 and I5 that way. Okay, I hope this is going to be useful. We're going to call it a day, and hope to catch you in the next one. Goodbye for now.